Hello everyone, my name is Brock. We are a team of three building Swap.cash, leading the overall development. So Swap.cash is a constant product market maker built on Bitcoin Cash. You can think of it as Uniswap for Bitcoin Cash. So you can do Bitcoin Cash to SLP, SLP to Bitcoin Cash, two-way swaps seamlessly and trustlessly, and now thankfully cheaply with Bitcoin Cash. So we are utilizing this magic constant formula where X indicates the number of Bitcoin Cash a covenant holds, and Y indicates the number of SLP token a covenant holds, and the multiplication gives us a value called constant in the purple color. So Swap.cash is made of pool covenants, and pool covenants have liquidity pairs. So for instance, here if we have a covenant state with 10,000 Bitcoin Cash along with 2,500 SLP token, and someone want to exchange 2,500 Bitcoin Cash for 500 SLP token, we end up with a state that holds 12,500 Bitcoin Cash and 2,000 SLP token. And the multiplication between pairs in every single state must give us this predefined constant value. So the constant value is pre-encoded into a script, and it must be the same value at the end of the script execution. That must be equal to 25 million, for instance, here. So we design a script, a custom script with around 300 lines of opcodes. And here's a very simplified demonstration. So we have three stack elements at the top. The first guy here indicates the number of SLP token a covenant holds. And then the next item, constant value, indicates the constant value this covenant is associated with. And then the SLP token identifier comes, for instance here for the 6DDF, this is the Spice token Genesis transaction ID. And then the spending path comes, the rest of script byte data. We have two spending paths. You either perform a swap or either add or remove liquidity. Right now we don't have liquidity path because of some limitations on the SLP protocol. You can do swaps today upon initial pool setup, which I'll do in a sec. So let's go step by step with our custom script. So as I mentioned, we have three stack elements at the top. First guy here indicates the SLP token amount, the covenant holds, the constant value, and then the Spice token transaction ID. And then the next step makes the preparations for the introspection. So we use check, seek, verify, check data, seek, verify, given signature and seek hash preimage. From the unlocking script, we make aware of the transaction content. And then we make a constant verification. So we fetch the amount of Bitcoin Cash this covenant holds, which is currently 10,000 in Satoshis. We can get this data from BIP143 seek hash preimage construction. We can access the value of this input in Bitcoin Cash, and then we fetch the constant value, which is 25 million. We fetch the SLP amount this covenant holds, which is 2,500 from here, for the first stack elements, and then we divide the constant value with the SLP token this covenant holds. That gives us the Bitcoin Cash amount this covenant holds. We don't have multiplication opcode, so we are using division instead. And this division result gives us the Bitcoin Cash value, and we compare the computed Bitcoin Cash value against the stored Bitcoin Cash value from the seek hash preimage. And if they match, we continue to execute the script. Then we do some extractions, output extractions. We make sure of the scripts, the seek hash preimage components or expected value, like things like components like sequence, hash type, log time, or expected value. Then we do make aware of scripts. So we not only make aware of transaction content, but we also make aware of scripts own content, the scripts own byte data. So here you can see on the unlocking script, we have script byte data here. So we fetch the script byte data, we hash this guy, and compare the script hash against the script hash, the script code from the fifth component. And if it matches, we continue to execute. As we do some splice operations here, we extract outputs. So we have 3 outputs. The first output is op return SLP metadata. The following output is the script new state Bitcoin Cash amount. The script new state hash, and the following outputs are the user outputs and change outputs. And then we do op return parsing. We parse op return the SLP metadata. We, for instance, make sure here the parse transaction ID is the expected one. The Spice token Genesis transaction ID from the third stack element. And then the spending path comes. So we have 2 spending paths, as I mentioned, either swap or liquidity path. If it's AA, then if the first element is AA, then it's a swap. Then we fetch the constant value from stack 25 million, and then we divide the constant value with the script new state holds 2000. We get this from op return parsing, and the division result gives us the Bitcoin Cash amount the script new state holds, and we compare this result against against the Bitcoin Cash amount the new state holds from the outputs, from the second output, the covenant new state. And then we compare it. If it's matches, we end up with this script SLP token, the new state holds, which is 2 bytes at the moment. We need to complete it to 4 bytes since we are dealing with 32-bit integers. And then we do we extract this, right? Then I extract the following the script byte data. So we have here, you can see one variable, which is the SLP token as the covenant holds. The rest are constant. The rest are constant, right? The constant value is constant. The SLP token ID is constant. Paths are constant. Only this guy is a variable, and we strip out this part, and the rest remains, and we concatenate them and construct the new script, the script covenant new state. We add the length file here, and we end up with the new state. We hash this new state and compare the result. Compare the script new state hash against the script new state hash from the output side. That is done through introspection. So we can also add or remove liquidity if the first stack element is set to AB. That's pretty much it with regards to how it works under the hood. So perhaps there are different things, Swap.cash and Ethereum Uniswap comparison here. So since Swap.cash built on an stateless UTX service model, Swap.cash can facilitate native privacy preserved coin-join swaps, which Uniswap is not capable of natively, at least. Since again it's a UTXO-based model, we can introduce a new path here called internal transfer path for native post office implementation, right? We can either do gasless internal transfers or gasless swaps, thanks to UTXO model, which is not natively possible on Bitcoin on Uniswap. And also there is something called pre-approval requirements on overall Ethereum architecture because of some initial ERC20 design choice. In order to interact with the other contract must approve the other contract. So here in UTXO model, you don't have such complications, so you can straight interact. You can make a straight swap at the first place, which I think simplifies the overall UX, just like gasless interactions. So throughout the hackathon, we built a web application with an interface so that you can type in how much you want to send and how much you want to get in the SLP token and hit the swap button. And so it opens up the explore.bitcoin.com. You can read the transaction details. Now we have a transaction with 2 inputs and 3 outputs. The first input, spending from the covenant old state, and constructing covenant NIF state in the second output. The first output is the SLP metadata. Second to first input is the Bitcoin Cash funding transaction that provides Bitcoin Cash in addition to transaction fee, and we construct the Spice token output on the last output. So from the front end side, we build our own custom wallet implementation built in with the front end. So we construct Zcash page image for each input. We are dependent on the ECDSA library for signing transactions. We sign the Zcash pre-image double hashes, then we construct the transaction hexadecimally, and then we, using the Swap.cash API, we broadcast the transaction back to the blockchain. So that's what we built so far at the CoinParty Hackathon. Thanks for listening.